Apologies, I tell you ahead of time, these lectures are very technical. They involve a lot of equations and modeling and so forth. And then we'll close out our time together talking about the geology of sequestration, and in particular, what are the hazards associated with sequestering carbon dioxide underground. And then we'll close with some comments about geoengineering, which are some proposals that many of our community have come up with to suggest how we might mitigate or deal with carbon dioxide in the atmosphere. So that's a little bit about our time together. I will say one or two things about the nature of the course. I will try to practice with you a couple of things that we do in Berkeley in the classroom. So while most of this is colloquium style presentation with slides, there will be times when you have to work with the person sitting next to you. So just be prepared for that. I promise I will not shame any of you in front of the others, but you will have to do some work together in the course of our time together. So the first part of our discussion is an introduction to energy and climate, which sets the stage for why carbon dioxide in the atmosphere is such a significant problem. So let's talk about the news. Of course, many of you have heard about the agreement in Paris that happened recently this last year. A great deal of activity and excitement over an agreement reached by many of the nations of the world to limit the amount of carbon dioxide into the atmosphere. It's been heralded as a really great agreement, and even the United States, at least at the moment, agreed to it. So 195 countries to limit the greenhouse gas emissions. The idea is to limit global temperature rise to less than 2 degrees centigrade. And the idea was to aim for 1.5 degrees centigrade. One thing that will happen as a context of this course is you'll realize that's impossible. We've already lost that goal, unless something very drastic were to happen, which is unlikely. Nevertheless, that was the ambitious goal set out. And then net zero emissions by the nations of the world by the middle part of this century. So by the time you and your children are in their teens, then this would be achieved. And then, of course, a framework for how to deal with nations that don't comply and say they do, and for review, constant review and updating. And perhaps most important is the notion that rich countries, which by and large have been responsible for most of the CO2 emissions into the atmosphere, would help the poorer countries by providing finances in particular to both adapt from climate change and to convert to, for example, renewable energies. So as we pose these problems this afternoon, the questions we have to keep in mind is, what does this mean, 2 degrees C? Where did that target come from, and why did people choose that? What about the equity issues associated with economics and science? Because, of course, we live in a complex world where posturing with regard to the environment is also a critical part of how decisions are made. How do we enforce and monitor what happens? And what if we can't measure the results? Or in the case of the United States, and I'm not happy to say this, but it may well be that measuring the results of climate change are not allowed. And what do we mean by clean energy? What does it in fact mean? And the picture is somewhat informative there. And of course, the whole point of this course is, where does carbon capture and sequestration fit in with respect to all these questions? So here's the big picture, the sort of giant overview of what's happening. We imagine a power plant producing carbon dioxide. Oh, sorry, I got to stay on the camera. Sorry. Okay. My apologies. Carbon dioxide stays from the power plant. We imagine a unit in which carbon dioxide is separated from the other gases. We'll learn more about that later. It's compressed, transported, and then injected underground. And that's the goal we have in mind. So who's the main character in the drama that's going to play out for the next 10 hours or so? And the main character is the carbon dioxide molecule, shown here with a variety of pictures from the internet. It's an uncharged molecule. It also has a quadrupole moment, as indicated by the charges in this particular picture. Carbon dioxide fits in this very funny place in terms of the energetic states associated with carbon. So I assume my audience is familiar with basics of high school chemistry. And so carbon in its highest energy state exists as, for example, coal or pure carbon. And the lowest energy state would be a mineral carbonate, often associated with the White Cliffs of Dover in England. And of course, carbon dioxide sits there right in the middle, and you recognize that there are very large energy barriers going from carbon dioxide to carbon and vice versa. And we recognize that chemistry tells us that chemistry tells us that the rates by which we go from this place to this place and back depends on temperature as well as many other parameters. So what about carbon dioxide? What do we know about it? And it's a relatively straightforward molecule. Here's a pressure temperature diagram, a phase diagram of carbon dioxide. And you'll recognize here we are, room temperature is around here. And we recognize that at high temperatures and high pressures, carbon dioxide exists in several solid and fluid phases, but that there's a supercritical point for carbon dioxide that's relatively low pressure and relatively modest temperature. And the reason that's important is because the best and most facile way to transport carbon dioxide is to put it in a pipeline and move it as a supercritical fluid. Its viscosity is low, its density is high, and it's relatively easy to manage. And so the fact that CO2 is accessible as a supercritical fluid turns out to be very important. We'll also discover in the geology of carbon dioxide that as we inject it underground, after about a kilometer or so, the pressure and temperature of the Earth is such that carbon dioxide would exist as a supercritical fluid anyway. So this phase diagram tells us a lot about where we're going to be going with regard to managing carbon. So here's the story that we have in mind. The carbon dioxide molecule will be injected underground. Because as a supercritical fluid, it's actually less dense than the brine or other rocks around it. Carbon dioxide will rise, and that's, of course, a potential hazard. If we're going to put something underground, we'd like it to stay underground and not come back to the surface. And we'll come back and talk about that in a few hours. But the idea is that the carbon dioxide molecule then will transport, but along the way, before it gets anywhere near the surface, it becomes trapped. And we'll find that there are 4 trapping mechanisms for carbon dioxide, and that there are many, many places throughout the world in which there are geological formations in which carbon dioxide is and can be stored stably. So understanding the geology and physics of this process turns out to be, of course, relatively important. As I pointed out before, the density of carbon dioxide varies a lot with pressure, so this is a cartoon which just reminds us that if this balloon represents CO2 at the ground, then if we put it underground, let's say on the surface, if we put it underground at 2.5 kilometers, we recognize the density is quite small, and really at just about a kilometer is when we approach the supercritical fluid phase. So as I said before, dealing with carbon dioxide underground is dealing with carbon dioxide as a supercritical fluid. So the notion that we were going to take carbon dioxide and put it underground is actually an old concept. These are old technologies that date even me. And this is because for many, many years, we have used carbon dioxide to enhance the production of oil. This is particularly popular in the United States, where carbon dioxide is injected as a supercritical fluid in rocks in which there's a modest amount of oil that's trapped. The supercritical fluid pushes the oil to a recovery well, and then the CO2 is recycled and sent back down again. Many, many thousands of tons of CO2 are used in this process to enhance the recovery of oil. So these kinds of chemical processes are already known and have been used for some time by the oil and gas industry. Here, for example, is a map of the United States, and shown on the map are existing pipelines for supercritical CO2 transport that have been built specifically to extract oil from underground. So the notion of putting CO2 in a pipe is not unusual, and the notion of pumping it underground is not unusual. There's a large existing infrastructure to make that happen. The idea that you could take natural CO2 out of a gas mixture and purify it is also an old technology. It's sometimes called natural gas sweetening. But if you follow this process diagram for a minute, look and see what happens out. Here you have a wellhead that goes to a well underground, and that's producing natural gas, maybe other kinds of fluids, but certainly natural gas. And they come up into this device, oil and water are separated. And then what happens is, in this column of this particular device right here, CO2 enters that is mixed with things like hydrogen sulfide. And as a result of this process, CO2 comes out, and hydrogen sulfide comes out separately. And then CO2 is then stored or used for enhanced oil recovery. and the hydrogen sulfide is often used to further make products such as gypsum. So the notion of purifying a gas stream to separate CO2 from other gases is well known. It's been used in the hydrocarbon industry for many, many decades. And the rest of this diagram just goes to show what happens to the rest of the gases, and ultimately you produce natural gas or methane, which is sent into the pipeline. So climate change has upended all these notions. And the reason it's upended all these notions is that the science, the technology, economics, policy, and politics are all completely overwhelmed by the scale at which we produce carbon dioxide. So while it's one thing to talk about enhanced oil recovery and natural gas sweetening, if you think about the scale of CO2 required to manage, it overwhelms all these fields, which is one of the reasons why it's such an enormous technical challenge, especially a challenge for China, India, and the United States, which we'll come back to in a few minutes. Let's take a look at the world energy consumption, because really it's all about energy, because as we use energy, we produce carbon dioxide. So here is a unit megatons of oil equivalent. We'll come back and talk about that, what that means in a minute. Here's the year up to 2012. And you can see the breakdown here that oil represents a significant part of it, and coal, a very large part of it. And then we see the emergence in recent years, just at the very top here, of renewables. And there are some countries, and we can thank Professor Blumich for Germany's leadership in the role of renewables, and other countries as well are making a very large difference here. Hydroelectricity is something some people have and others don't. It's also very difficult to manage. But if you look at this graph, you recognize that a significant fraction of the world's energy consumption is related to oil, natural gas, and of course coal. So today we are at 13,000 megatons of oil equivalent is our energy consumption use. And so now we have to sort of get our mind around it. If you're a chemistry student or a physics student, the numbers associated with this are absolutely staggering. So a TOE is a ton of equivalent oil, which is the energy released if you burn a ton of standard oil. That turns out to be 42 billion joules. So the world energy consumption is 13,000 times that. That's a lot of kilograms of equivalent oil. And if you ask, well, how big is that per year? And if I take the density of oil, as I might find in a textbook, I discover that we have 2.5 cubic kilometers of oil equivalent per year are being used just so that we can generate the energy we use every day in our lives. That's a rather enormous amount of oil equivalent. Another way to look at it is one of these 13 million ton equivalents and 14 billion joules work out to in other units. These are popular units for engineering and other disciplines, that many kilowatt hours, that many BTUs. And it turns out in the energy field there's a unit called quads, the quadrillion BTUs. And so this is the number that you often see when you read the popular media and you read the newspaper about energy equivalent. They often use the units of quads. And you can see that that's a lot of energy. So let's take a look at the scale. Here's a log scale for energy in joules. And here's some of the things I'm familiar with. So a bicycle ride from Berkeley to San Francisco, our typical lithium-ion battery. And you can see the energy associated with these on a log scale. And we notice that the output of the sun per second is up here. So that's sort of one extremum, as it were, right, of energy. But if we look at, for example, things we've read about, here's the Japanese earthquake and tsunami that happened a few years ago, devastating effects associated with that. And here's our per capita energy use, right here, and so forth and so on. If you look at the scale, recognizing that it's a log scale, you see the staggering numbers associated with our energy production, and indeed with just the things we do routinely, such as boil water to make a cup of tea. So here's the annual world energy use right there. So we are burning the equivalent of this many tons of oil per year, and we can take stoichiometry. This is the chemical formula for a typical oil. Here's how much oxygen would be consumed, the amount of carbon dioxide produced. And if we turn out, that turns out to be a lot of carbon dioxide. And we're going to come back and revisit what those units are and various things along the way. So that's the mass of carbon dioxide, and that also is the mass of carbon. So as you read the literature about carbon dioxide in the air, what you find is that there are graphs that contain the mass of carbon dioxide in the air or the mass of carbon. The units are often mixed up, so as a student you need to pay careful attention. The mass of carbon in the atmosphere would also include methane. We'll come back and talk about the role of methane in climate change shortly, whereas mass of carbon dioxide, of course, is just that. And there's the stoichiometry of the fuel. So here's a million metric tons of carbon released from the burning of our fuels, according to the various kinds of industries, as a function of year. And here we are in 2010. And of course, you can see the total is really quite alarming. So almost 8,000 gigatons, as it were, of carbon per year are being introduced into the atmosphere. So I don't know how to convince you, maybe when you're with your friends tonight over tea and talking, what does it mean 8 gigatons of carbon per year into the atmosphere? Even though the atmosphere is a very big place, it's a staggering amount of carbon. And there you see that, for example, things that students often don't realize is that cement manufacturing is a huge energy consumer and it's a non-trivial contributor to carbon dioxide into the world's atmosphere. And so you find that chemists and chemical engineers in many parts of the world are looking at technologies for reducing the CO2 emissions from cement manufacture. So here's a nice picture of our coal-fired power plant. And so the question you might ask is, well, if that's CO2 coming out of the smokestack, how much of that can we actually capture? Because there are many producers of carbon dioxide. For example, your vehicle. Are you going to be able to capture carbon dioxide from the exhaust of your vehicle? So let's take a look, and I have these numbers for the United States. Might be interesting in all your spare time, students, to think about where you would find these numbers for India and have them at your fingertips. So here's electrical power is 28% of the U.S. energy related sector. Transportation, another 25, and then you see these here. And now, if you look at the energy related source, according to the fuel, you realize petroleum, coal, and natural gas more or less split equally, although petroleum is a little more. But the coal sector, which provides electrical power, is certainly the easiest place to imagine doing carbon capture and sequestration. The coal-fired power plant is fixed, and it represents a very large producer of energy. These diagrams are produced by the Lawrence Livermore National Laboratory in the United States and published every year. And what they do is they represent the flow of energy in our systems and what they are used for. So for example, here's petroleum, and the units are not so important right now, but you can see this is 35, a rather large fraction. And you see that almost all of that is used for transportation and a little bit of is industrial. So these flow diagrams help us understand a great deal as to where the carbon dioxide is coming from and where it's going to. And here you see coal right here at 19.7, and this bar goes right to electricity generation. So coal is a natural place to think about working with carbon capture and sequestration because it represents a fixed in place source of coal, and it represents a significant part. So the other issue, of course, is how efficiently do we convert energy to electricity. That's another sort of irritating matter because the efficiency is typically on the order of a third. That's the Carnot efficiency, largely associated with boiling water and blowing turbines. And so we use a great deal of coal, and yet we don't produce much electricity from it, and therefore a lot of CO2 is produced. So what percentage of our electricity generation comes from coal? In the US, it's about 45%. In Germany, it was higher, and now it's, I think, only a third and falling rapidly. And I actually don't know the numbers for India, but I'm sure they would be interesting to find out. So here we have sort of CO2 emissions from sources. These are European numbers now. Those that are addressable by carbon capture and sequestration, that is, they come from a fixed source like the cement plant or coal-fired power plant, stationary sources. The transportation sources are untenable to capture right now, although I've been to a conference recently in which some of our colleagues from Europe, they claim they figured out a way to capture CO2 from the tailpipe of a car in a sustainable way. I don't know the details. I'm curious to see how that could work. So if we take coal, so if you take stationary sources, about half of them are from coal, and then here you see the cement industries and so forth. So it's clear that carbon capture and sequestration from stationary sources and coal also makes sense in Europe. So we should start with the existing power plants, okay? Because those are in place already. So now I would like, this is one of your first exercises. You need to introduce yourself to the person next to you. And just take a minute or two, would you please, and ask these questions with your colleagues. And then we'll come back in 1 minute. Please. Okay, let's come back together for a second. I'll come back and visit these questions. I'm just wondering, would anybody care to tell me anything about these numbers? Does anybody know? A list where you would go to find out? Yeah?
So like, if you ask me the energy percentage from the coal thermal plant, it's around 40-45%.
So it's about the same as the US?
It's about same, maybe a little bit more than that. We have, right now, we have government thermal power plants. Two are in Bathinda, one is in Ropar. It's a 2 district, 3 plants. And recently, in the last 5 years, we put 3 more thermal power plants. One in Amritsar district, one in Rajpura in Patiala. So we have now, I think, 5 thermal power plants in Punjab. It's a very small state, with a very small area as compared to India. And if you ask about that hydroelectric power plants, we have one on the border of Punjab, one and two. One is in After Dam, another 2. So I think we have, now we are also going for solar plants. And recently there is one power plant, it's a solar-based rooftop, that's world's largest one, is opened up in Beas. Just 6 months back, around 6 megawatts. And one to another plant, 25 megawatts. But it's a small as compared to, if you compare this one, because they are about, some are 800 megawatts, 600, 1200 megawatts. So this is somewhere, but still now we are moving more towards the non-conventional resources. And the share maybe, we don't have very good data sources for these things. So this is all about.
So somebody knows a lot here, so thank you very much. Okay. Good, so if we go back and look at stoichiometry and the combustion process, and we ask ourselves, what is the form of carbon that we're likely to see? So here's a table which I took from the internet, which lists the various kinds of carbon. Their so-called heating value, and of course the heating value tells us how much heat you get per pound or per kilogram of this material, and that's directly related to its heating value and its source as electrical power generation. So for example, anthracite, which is this sort of very dark-looking black coal, has a relatively modest heat of combustion. So we have the stoichiometry of the fuel, and then we have the emissions per BTU. And so we can figure out then the various types of coal. And I just wanted to call attention to the fact that, for example, lignite has 200 pounds of CO2 per million BTUs of energy. That's an interesting number to know. The other interesting number to keep in the back of your head is that natural gas is not quite half the CO2 emissions that coal, for example. And so this is one of the reasons why the United States has recently looked like such a favorable player in the carbon emissions world, and that's because of, for economic reasons, not policy, for economic reasons, the United States is moving many of its fixed power generation to natural gas, and as a result, the CO2 emissions are falling. But it's not because of a policy, it's because of the tremendously cheap prices associated with natural gas which derive from various processes to produce it, which we'll come back to when we talk about geology later. So, different fuels have different energy contents. And so what that means is that if I look at the amount of CO2 produced for the amount of energy produced, I have these various characters, and you'll recognize that coal, again, is the highest value. So coal produces almost twice as much CO2 as natural gas per unit of energy. So let's take a particular coal-fired power plant in the USA. This is one in the southeast part of the USA, near the state of Georgia. This particular coal-fired power plant burns 1,288 tons of coal every hour. It's a staggering amount. And one way to think about that is that either 2 to 5 trains per day full of coal arrive at this power plant, and each train has 124 cars that are filled up with coal. It's just a staggering amount of material that's being consumed each day for this particular power plant, and I think this is a 500 megawatt unit. So how much CO2 comes from one particular power plant? It's a figure that's nice to have around. Let's take a medium-sized 500 megawatt coal-fired power plant. That's sort of the generic one that you might find. And then you have to do some unit conversions to look at how much energy you get out of coal, the efficiency of the power plant, the stoichiometry of the combustion, and that turns out to be 70 cubic meters per second of carbon dioxide. So it's an interesting number to have at your fingertips. I'm going to guess that this room, it would be an interesting exercise for you to figure out how many cubic meters this room is, but I'm going to guess it's on the order of 100. So you could imagine filling this room with carbon dioxide every second, 24 hours a day, 7 days a week, 365 days a year. That turns out to be 4 megatons of CO2 per year from that particular power plant. And of course, you can scale according to the size of the power plant. So you can just take this number, multiply it by 6 to figure out a 3 gigawatt coal-fired power plant. The largest, I think, in the USA is a 3 gigawatt one, although I think there's a 6 gigawatt one coming online relatively soon. So it's a staggering amount of CO2 per power plant. So another way to think about it, which makes sense to students in the USA, is that if you take the Empire State Building and imagine it as a hollow rectangle, then it would fill with CO2 every 4 hours just from one particular coal-fired power plant. And so that's the scale that we're talking about. And you might ask, well, how much is that per year, or for that matter, the lifetime of a plant? Because the lifetime of a coal-fired power plant is 30 to 50 years. So that's an interesting number. We're going to come back and look at a diagram for that a little later on. But another question that often comes up is, well, are we going to run out of fossil fuels? Are we just going to be working with renewables any day now? That any day now has been moved further and further away in time as both our energy efficiency increases and our ability to extract resources from underground improves. But here's a typical diagram. We call it the carbon age now. Here's this particular is the carbon stocks in the ground and in the atmosphere, and we see that an enormous amount of CO2 is projected. 2100, so how much of these fossils are in the ground? So here's the other half of that diagram, and we realize that gas, oil, particularly coal, there are enormous stocks of coal underground, and it's unlikely that we will ever run out, really, to be honest. We can't, projecting more than 100 years in the future looks like science fiction. So, but we have a tremendous amount of resources underground. So the answer is, when will we run out? Well, we'll run out of patience first. But these known reserves represent, if they were all burned, 4 times the emissions of CO2 into the atmosphere to date, and the consequences of that are amazing. I found this interesting quote by a Saudi Arabian leader in the oil industry. During the 1970s, there was a famous embargo in which the prices of oil skyrocketed. And he made this quote that I find very interesting, that the Stone Age did not end because of the lack of stones, and the oil age will end long before the world runs out of oil. And I think that's a very interesting prediction. Let's take a look at another view of it. Here's the fossil reserves in terms of the gigatons of carbon Here's what's in the atmosphere right now, and this would represent about a 2 degree C temperature increase. So you can imagine the consequences